Morning, doctor. Morning.
Thank you, thank you. Morning. Okay, this is week 7, huh? Week 6, sorry, week 6. Okay, shall we have our class assessment next week?
Okay, doctor.
Yeah. For next week, because I have my student candidature defense, and next week. Let me think how we're going to do about it. I think I can convert it into Google Form, all right? Google Form. So you just answer in your Google Form. Is that okay?
Okay, doctor.
Okay, Google Form. Okay. And then that one next week will be week 7. Then you have semester break, isn't it? Or you have semester break in week 7. Anybody knows? Because
Week 10,
sometimes they
Doctor.
change the. Huh?
Week 10, week 10.
The same? Week
Minggu
10.
ke-10. Minggu ke-10.
Minggu 10. Minggu 10 your semester break, huh?
Yep.
Okay. Hmm. All right. So we have
All
next week 7, week 8, because we have add puzzle that we have not done. Uh, I hope we can finish this so that we can go back to tutorial past year questions. Your exam, your summative assessment will be actually together with other lecturers as well. So it will be conducted at the same times. Huh? Conducted at the same times. I hope, I don't know if they're going to do it. I hope they do it separately. So your answer script can be passed straight to me, right? And we have ample time for tutorials and for your add puzzles and for your class tests and so on. Okay, so I've been actually trying to finish it by this week, hopefully. Okay, and then we have time for your tutorial. I don't want it to be rushing it. Then we don't have time at all. My previous lectures, I don't have enough time, right? So we spend more time on our lectures. But now we are the end of the topic on the medical applications, right?
Doctor,
Yes.
someone's tried to join in.
Okay. Thank you. Hold on a sec. Yep. All right. We have 21, so we have everyone now. Okay. Those that just join in. Okay. Those that just join in. Just to remind you, next week we have class assessment test. So only 2 topics, photochemistry and the first lecture note and the second lecture note. So please read through, right? Not that difficult, I think, my parts. Okay. And following week, after week 8, week 9, week 10, we can have head puzzles and which is on your own. And then we can have tutorial as well. So that will cover my topic. So I'll try to finish it today, and all this topic in photochemistry. On the applications of photochemistry, we are focusing towards medical applications. Right? Is that okay?
Doctor, just to
Yeah.
remind you haven't uploaded your notes yet.
Yes. Thank you. When you said that, yeah, it remind me. Okay, thank you. I do it straight away after this. Yeah. I've been doing other things. Um, Thank you for reminding me. Right. Any other things with regard to the test next week? The reason I have the test next week because I have candidature defenders that just joining in. Don't forget your attendance, please. Right. Don't forget your attendance. Okay. I record as well this over here, but at the same time I have your attendance. Right. I have to stop. Okay. Let's go back to our class. Now, basically, in another 40 minutes or so, hopefully we can cover our class for today. And today is on the medical applications. Just tell you the truth. Half of this lecture notes, not half, 1/3 of the lecture note actually have done some of the photochemistry work for medical applications, right? And the rest is not half. They are not mine. Right? Mine is more on besides liposome that in this topic that I included a little bit. The rest is on X-ray as well, which is not included in this lecture note. On X-ray using rare earths, just to monitor patient exposure by the X-ray, and but the work is almost, some of it is what I'm doing, 1/3 of it, and the rest is not never done on the up conversions and nanoparticle because of we don't have that facilities. I would like to do it, but well, at my age, I have another focus on my research. Wish I could actually do that type of research. That's what I did a long time ago, and didn't have time to go back to that particular research because of the facility. And let's go straight to the lecture notes. Okay, just remind those, right? 21st April, Wednesday, right? Online. So I just put everything into Google Form. Okay, you just answer straight into Google Form. Okay, same times. Okay, same times on Wednesday. Right. If there's a calculations, I'm going to ask you just give the answers, but you have to do it step by step because step calculations that step need to be put into your answer as well. Right. So there is no problem, I think. With regard to your exam. Now, when we talk about up conversion nanoparticle, especially in medical application, you can Google from the internet quite easily because we are talking about simultaneous absorptions of photons. So not only a single photon, but it can be multiple photons at the same times. So if you look at what we have, typically the absorptions, right, it's around 972 nanometer. This one is erbiums, right? Erbiums, 3+ erbium. So I was working on erbiums. Okay, I was working on erbium. This is a rare earth. In your yes.
Sorry to interrupt. You're not presenting anything.
Oh, you're not seeing anything, huh? Thank you.
Okay.
There you go. I need at least. There you go. You don't see my screen.
No, we
Okay.
cannot see your slide.
Right. Yeah. Right. Did you get my screen now?
Yes.
Okay, thank you. Because I do not open. I was my other computer actually just running and loading, so not having the other computer on to see whether you have my screen or not. Yeah, it's the let it be. Right, now you can see my slide. Right, let's go back. Okay, this up conversion nanoparticles, normally people as you see NP. NP is normally represent nanoparticles, right? Nanoparticles in medical applications. In this case, if you look at it, you can have example absorptions, photon absorptions for up conversions nanoparticles, and the particles normally made up of. We have example here, right? Sodium, yttrium fluoride, terbiums, erbiums, or erbiums, right? So I mentioned earlier on, I've been working on erbiums, right? Both for telecommunications as well as for medical applications. Why erbium being used in telecommunication, especially because it can actually increase the signal amplification of the signals from the signal source and amplified to the receiver. So during the time of you sending the signal, you might lose some of the signal. So you need a device that actually amplify the signals so that you can hear much clearer on the other side of the line. And in medical applications, erbiums are used to detect the exposure of X-ray radiations. X-ray radiations, so you can use the erbiums. But monitoring, you need to do it almost, as fast as possible, not too fast. You know, you do it almost immediately because you might lose the signal from your materials over time. So at the same time, you have the time and exposure, how much being exposed, and so on, and whether the exposure actually reaching to the side of the one that you are monitoring. So that's one on erbium. So we have the yttrium fluoride, sodium yttrium fluoride, terbiums and erbiums. This is nanoparticles, right? Okay, very small nanoparticles. You can see this several emissions at 410, 525, and so on. Right? This is you can have multiple photon absorptions. Now, maybe in my lecture note there's some changes compared to the one you have. Okay. Again, I have two. I owe you two now. And I share with you this one as well. When we talk about bioimaging, especially we don't want it to be, you're not sure what color it is. People like me who is slightly colorblind, you put, for instance, yellow and green very close, so I might not be able. If it is not certain of yellow or green, so I'll not be able to actually differentiate. So but by using this up conversion nanoparticle, it's just like metallic. If you have metal emissions, you have one line of emission, which is very specific to the elements that you are studying, right? Whether it's iron, copper, and so. Right, you have line emission, so very specific at certain wavelength. Up conversion nanoparticles, one reason maybe because the size is very small. You compare to organic dye. You look at the bottom. Let me get my. Right. So the organic dye, your bottom left corner, right? You got bottom left corner. The half width, which is this is sigma, okay, 2 sigma here. The half width height compared to quantum dot, for instance. This is quantum dot. Sorry, is there any quantum dot here? So this is quantum dot. Quantum dots, right? quantum dots, this is also very small particle. If you look at quantum dot, cadmium, or a lot of people doing zinc sulfide, easy to produce. So last time we also produced zinc sulfide. Less than maybe few nanometer, 20 nanometer. And the emissions much narrower than the organic dye. But compared to up conversion nanoparticles, right? Okay, if you look at half width, half width. Okay, the half width. Okay, dye is much greater, right? So you have smaller for quantum dots. For nanoparticles, the half width is even narrower, right? Very sharp and narrower. Up conversion nanoparticles. Okay. That's why people working on this up conversion nanoparticle, because it's very much well defined or narrow emissions. Right? So in this case, I just give you example of the sodium. Oops, sorry, I don't know. Sodium yttrium fluoride. These rare earths could be terbium I mentioned just now, or terbiums, right? Rare earths. Right? So if you monitor the emissions, of course, this is a typical some of the work is studied, and you can just Google in that if you want to have an extra reading, right? This is the difference between up conversion nanoparticle as compared to even quantum dot that last time was people are into research of quantum dot, but now new type of materials, right, coming out, the up conversion nanoparticle. And so now people, instead of working on quantum dot, that is for electronic, right, for medical application especially, we are working on more towards up conversion nanoparticles. Okay, and we take another example. I just give you an example for the up conversion nanoparticles, right? This one actually employing, if you heard of hyaluronic acid or hyaluronic acid being used in cosmetic, especially, right? So the up conversion nanoparticles, you can use terbiums, right? Terbiums, so the yttriums, fluorides, right? Yttrium fluorides, okay, and typically coated with the hyaluronic acid. Okay. So you notice the previous slide, you can have many emissions, right? So one of the advantage of this up conversion nanoparticles, right? Up conversion, right? You can fine tune, right? You can fine tune the emissions, right? So by the exposure to the laser lights, or even you can modify the composition of your nanoparticles, right? And typically in medical applications, or if it involves biological samples, normally we are working in the near infrared light. So because it is again, it's a low energy, but you have advantage in the depth penetrations, right? Low energy and advantage in depth penetrations. Right? So if you compare to UV visible energy, okay, and the infrared. Oh, this is something. Hold on a sec, because it's coming up. Oops. And another advantage of up-conversion nanoparticles, because we are using the near infrared, it is more biocompatible, right? More biocompatible. We are talking about 700 to 1,000 nanometer, right? This is actually low energy, right? This is very low energy, okay? So if you pump in the UV, then of course you're going to have the adverse effect if you are using the UV, UVA, B, or much higher energy UVC. Right? We don't want to use UV. So infrared, near infrared is much better compared to much higher energy to be used in biological samples. Right? So if you look at, and there's other advantages as well, right? Other advantages using this up-conversion nanoparticle, employing the near infrared radiation. Okay, and for some cosmetic or transdermal delivery, this is through skin. Yeah? If you are using nanoparticles or the work that I'm working on liposomal, which is very small, if you're looking at how much penetration and so on, so we can actually spike with small particles, right? Up-conversion particles, just to look at how deep the penetrations. Of course, we can use the not the human, so far biological sample. Right? Okay, so this is just an example on the right hand side. Take a look at some of this one actually taken from one of the articles, right? So how the up-conventional particle being used, typically hyaluronic sample, right? So you have particles coated with the hyaluronates or sometimes it's mixed together. So most of the time, because the nanoparticle is very small, right? Nanoparticle is small, so it coats around. And during the productions, you may start with a nuclei of these materials, right? Nuclei is very small. If you introduce hyaluronate, for instance, so you may have some assembly. But two nuclei can assemble. Two nuclei can assemble to form doublet, quadruplets, and so on. Then particle become much larger still in nanometer, very much small. But when I said nuclei is the first yttrium, fluoride, ytterbium, for instance, right? Single crystal, not single crystal, the first start of the crystal. So they may actually aggregate, so forming much larger particles. So particle actually made up of many crystals. Right? One particle, we take example of this particle, for instance. This one made up of many particles. Right? If you're talking about 10 nanometer, for instance, 10 nanometer of up-conversion nanoparticle made up many crystals, and some actually not forming crystals, some are amorphous. Don't expect you have 100% crystal, so you may have like 30-40% of crystal inside the nanoparticles. Right? So this is using these nanoparticles, right? We can actually detect, search, and destroy kind of system. Okay, so it absorbs light and destroy the tumors and actually release the energy to the neighboring tumor cell, for instance. Right? So in this case, you can use the photochemical therapy. It's just my pen. I need to. Oh, I can go up and down. Okay, sorry. Right. So typically, you may have the what do you call it? The antibody, right? An antibody antigen. So this particular amino group actually will attach on the site of the cancer cell, maybe, right? So this one talking about tumor cell. So the amino part actually, this one actually targeted delivery kind of treatments. So targeting straight to the cancer cell, right? So if you look at the emission, I just give you an example. For instance, in this case, right, the tunable, the emissions can be tunable, depends on the energy that you pump in, as well as depend on the materials. In this case, the up-conventional nanoparticles, right, we are using 980. This is near-infrared energy, right? So we may have multiple photon absorptions, right? That can be tuned, or you can take certain emissions of the lights, and you can have filters and so on. Or you can just change the compositions, and you have particular emissions for your up-conventional nanoparticles, right? So this is just look at the what happens, right? What happens when you introduce or in vivo analysis of your up-conventional nanoparticles, right? So you expose with 980 nanoparticle laser, right? And then you can actually observe, right? Observe the light emissions, right? The light emissions by looking at the fluorescence, and this particular emission actually after you introduce this is through the skin, transdermal delivery, which is you introduce through the skin, right? Like you may have a cream or patch and so on, right? This is transdermal delivery. So with this technology, we can actually help doctors to diagnose or to recognize, or because some of the cell cancer, they can metastasis. Metastasis means imagine the bone cancer, for instance, right? On the bone, maybe on the leg, right? So you may treat the bone cancer on the leg, but then the cancer cell, the osteosarcoma, the osteoid, which is before it formed the cell, right? The osteosarcoma, actually cancer cell that produces the osteoid, and the osteoid may be in our blood, in our blood, been transferred along the body, So if we can recognize this with this technology, we can actually recognize where the osteoid is, because it is actually fingerprints of the osteosarcoma. We're talking about cancer of the bone on the leg just now. And the problem with the osteoid, it can actually go right up to the lung, and then when it reaches the lung, more osteoid actually accumulate and then forming like a bone cell in the lung. So this is metastasis from the bone, right, migrated to the lung. This is very common in hospitals, right? In hospitals, and patient normally once we able to diagnose, is too late. When we able to diagnose, it's already too late, because the osteoid in the lung accumulates and forms bone fragments in the lung. So this is eventually the patient will be suffocated, cannot breathe, right, because of the formation of this osteosarcoma in the lung. This is called metastasis from the bone to the lung. So it's very common. So it's quite unfortunate, So we hope, this kind of thing, maybe you in the future also can help to reduce or to cure this cancer disease that people experience. Is our responsibility actually. So and it can be actually detected, and you can find out where it is from the beginning. When you can detect using X-ray or using CAT scan, it's already almost too late. X-ray is too late because X-ray is much bigger object compared to CAT scan. CAT scan is much smaller object. That's why some doctors prefer to diagnose using CAT scan, not just the X-ray. But again, as I mentioned, in the blood itself, I think everyone has. But it's just that how sometimes unlucky, right, that you have growth of this cancer cell. All right. And the next application actually using the upconversion nanoparticles in the liposomal drug delivery. And there's a short form here. So normally this is drug, okay, delivery system. You can see my writing, right? Okay, drug delivery system. Excuse me. And the advantage of this the liposomes, this is actually bilayer membrane made up of phospholipid, similar to make up our cells, but our cell has protein, other things as well. And you may have a simple form of these liposomes, the liposome. So it can carry, high load of drugs and then release it in the area whereby it is required. It can be targeted, right? Just like what we mentioned just now, the amino group, right? So can actually target to the receptor, for instance. So what we are doing actually, we are more focused on targeted drug delivery at the moment. So on Thursday, next Thursday, and this Thursday, my students will defend her PhD. So quite unfortunate that yesterday my colleagues for this particular student passed away quite sadly, and I think a bit sad to have colleagues that I've known for many years suddenly disappears forever. And so these liposomes, right? It can carry a lot of drugs. This is the drug. Take example of this is the drug. It can carry a lot of drugs inside and outside as well. And you can encapsulate, because the size of liposome, right? It can be nano size, can be up to 100 nanometer, 200 nanometer. Right? At the same time, you can also encapsulate nanoparticle, upconversion nanoparticle in maybe 10, 20 nanometer size, or much smaller, maybe 5, or 6 or 5 nanometer size. For upconversion nanoparticles, for metallic particle like silver, another example of quantum dot particle, for instance, we can produce it in like 3, 4, 5, 6 nanometer size on average, which is very, very small, very small. And with this size, you can actually put it inside these liposomes. So in this case, this is doxorubicin. Doxorubicin, this is for chemotherapy drugs. Chemotherapy drugs. Normally, this one is very toxic. This is a very common drug. It's used to treat cancer patients, but unfortunately, this is at the same time the free drug. So this one is free drugs. Free drug. So all without anything, without loading is free drugs. One is load. This is slow release. Right? It's not a free drug. Slow release, though, you can actually, why you do this? Because it can actually reduce the toxicity of the chemo drugs. Most chemo drugs, they're very toxic. That's why you notice patients are not prescribed with one drug. It can be prescribed with antibacterial drugs, for instance. It can be prescribed with antifungal drugs. At the same time, being prescribed with to treat the adverse effect of the drug itself. So patient normally given like 3, 4, or 5 different type of drugs, depends from one patient to another, just to actually treat the patients with what's going to happen, and including to treat the side effect of this chemo drugs. So with this, you can actually minimize the side effect. And where is it now? So again, this actually using near infrared, right? Near infrared, that you have azobenzene liposome up conventional particle hybrid vesicles, right? For control drug delivery. Why is control? Because the drug actually being released since this doxorubicin is toxic, right? Since doxorubicin is toxic. So you have to control drug delivery so that it's not first exposure to the patient, but a small amount at a time. Right? When the patient is exposed with a small amount at a time, it can actually minimize the toxicity of the drug itself. So and these azobenzines, right? The azobenzines, this is the azo, right? The azobenzene. So the azo with this, right? It can actually absorb the blood energy that being exposed, right? And then release the energy to the vicinity at the same time exposing, releasing the drug as well, right? Right. So the next example is actistane. If you can get this from the internet easily, right? Normally, people use in medical applications. People stain the cell, right? You can use the actistane 48. You can have 5R5, the actistane, for instance, and 670, for instance, right? This is on the amino acid itself, right? So actistane antiquilin rats with Sid3003 cells. This is how the cell actually being produced, the protocol cell being produced, right? And we have DAPI here, right? We have DAPI and F-actin, right? F-actin actually the site, the amino acid site that the F-actin actually receive, because the interaction between this chemical compound with F-actin, right, used in this staining of the cell. Right. This is not in your lecture notes. It's I thought I just grab one just here, since there's I forgot about the DAPI blue. This is DAPI, right? This is DAPI give you blue emissions, right? This is DAPI give you blue emissions. So the chemical structure diamino to phenyl indole. This is indole. You have indole, right? So this is dihydrochloride. So this is a salt form. So this is a salt form, right? Salt form. So you have positive somewhere, right? Either this one N or this two N, right? The salt form. And basically the molecule actually receive in between the protein amino acids, the protein amino acid. So in this case, the DNA and the interaction. So it's very specific, especially. So that's why people are using this typing for staining of the nucleus, especially for staining of nucleus. So you can stain the cell, you can stain it with DAPI, you can stain with different staining agent for the surrounding and so on. So you can actually look at the cells and you know which one actually containing the amino acid, or in this case, the nucleus, for instance, right? And which one actually the phospholipid of the cells. They contain a lot of phospholipid of the cell. Okay, quite straightforward actually. Once you know what suitable molecule to be used, and the rest is quite straightforward. On the right hand side, it's just molecular modeling, interaction between the DAPI and the DNA. Right? And just now we're talking about colloidins, prophos. So similarly, palloidin also, this is F-actin. So this is the amino acid, basically ribbon structure, ribbon structure of the amino acid. Right, and then we can see where the colloidins, prophos actually receding. Okay, in the F-actin. So this one, colloidins, we have I think how many? 6, 7, I think amino acids in this colloidins. Yeah, around 7. Okay, this is the fluorophores of the one that actually emits light. There are light emissions. So the F will recede on the F-actin of the amino acid of the cell. So this one, trimethyl rhodamine, 0.8. So this is rhodamine. Rhodamine. Normally we use rhodamine for lasers. Lasers, tunable lasers, tunable dye lasers. Normally using rhodamine 6G especially, right? Because the energy can be tuned. Why? One of the reason, we can actually produce many emissions. So that's tunable laser using rhodamine 6G. Can I speed up? Right. So the bottom one, I think I just I add another image over here, right? The new one. I just get it from internet. So just put it in the existing slide. So this is an example of staining of the amino acid, right? Staining of the amino acid. Okay. So see, again, I cannot see. There's a red color inside a bit, right? So stain with anti-vigilin red, right? The T cell, right? DAPI for nucleus, right? So you can have different staining, so you can see exactly where the nucleus is and so on, right? Right. So this is another example of photochemistry used in the medical application. So I give you some example over here so that you can read up and the importance of photochemistry, not only in chemical synthesis, right? Not only in chemical synthesis, but actually helps a lot in medical applications for the doctors to diagnose the patient. Sometimes it's very difficult just to run a blood test for detections. It's actually more similar, but it's much better if you can actually visualize it using staining agent. So typically, even people in medical, in biology, they use this staining agent for staining the cell, right? Okay, and another examples, right? This is the last example for photochemistry application in medical. Breast cancer basically very well researched cancers compared to other cancers, including maybe colon cancers, other carcinoma, bone cancers, and so on. So breast cancers is one of those very much well researched, and the understanding, the theory behind what happens in the breast cancer, what's going on, actually very well researched and very much well understood compared to other type of cancers. Right, so breast cancer is very much studied. Typically, in a breast cancer, we normally looking into HER2. I'm not sure where is it. Yeah, here. We're looking at the HER2 because this one actually overexpressed. This one's overexpressed by the cancer cell, by the breast cancer cells. So when you have overexpressed, we can actually focus on the HER2. And if you have targeted delivery, very much targeted to be, because just like any other drugs, if you just take even simple as paracetamol, one tablet of paracetamol may be 500 or 600 milligrams of the paracetamol, but not necessarily 500, 600 milligrams of paracetamol actually being absorbed in your small intestine. At the same time, not all once being absorbed systemically, which is into the blood stream, not all of those that though being absorbed into the systemic absorption into the bloodstream, not all the paracetamol actually goes to what is supposed to be intended for, right? So only small fraction actually that is biologically available for treating your problems. So this is when you have targeted delivery. So especially we have HER2 here, which is being overexpressed surrounding the cancer cell, right? And the delivery will go straight. It will be maybe in the bloodstream, for instance, but then if it is targeted delivery, it won't be released at any other places except when it meet this overexpressed HER2, right? It will actually lock into HER2 and then absorbs by the enzymes and the drugs taken in that particular area. Okay, so the adenocarcinoma, which is cancer cell, in this case, very much established. So we can use the upconversion nanoparticle as well. In this case, same thing, what we learned before. Right? We've been using this, right, to target specific towards this breast cancer treatment. Right? So and it can be detected, much early, and at the same time, it can be used to actually treat breast cancer patients. Right? So since breast cancer actually very much established, so this is one of the work actually, I think, and there's a potential as well. Right? There's some applications. Right? In this case, right, this phantom is not a real human cell, right? Basically, we mimic the, if it is for the breast cancer, which mimic the same human physiology, right? And then we see how the upconvolutional particles actually functions for treatments of this breast cancer. Okay, so I think I covered that. Okay, guys, I covered my topic. Right? Some applications, guys.
Yes.
Right. Okay, so you may have class. So don't forget next week topic, first lecture and the first lecture notes and the photosynthesis topic, right, for the next week assessment, right?
Doctor.
Okay, doctor.
Doctor.
Okay.
I have questions regarding the drug and you already right. You encapsulate the drug, the chemo drugs, and the UC and the
Yes.
unconventional mango in the bilayer,
Yes.
and you put into the streams, right? And when
Yeah, it can be intravenously introduced.
and the bilayer reach target, you shine UV light on the bilayer, and the nanoparticle absorb the UV energy and release it out and trigger the breakup of the bilayer. Am I right?
They are one of the work that be done. Actually, the particles actually releasing the energy that kills the cell, right? And
I want.
okay. There's more complicated than that.
Okay.
It's more complicated. Okay. First, anyway, to ask, I try to actually answer it in as short as I can. Okay. The liposome need to be protected from our body immune system, from the white blood cell. There's if it's intravenously and not being protected, so our white blood cell going to destroy it.
Yes.
So we need to camouflage. We need to stealth. It has a stealth property, like a stealth fighter. Nobody can detect. Okay, that's another research by itself, another method. So, and on the surface of liposome, you have this antibody, for instance, right?
Okay.
That targeted specifically to the HER2 receptor. It's very specific. If not specific, then it's very difficult. It goes and everywhere, right? It's very specific, right? And liposomes or maybe other particles, right, that containing the upconversion nanoparticles. Okay. Once it lodged into this HER2, which means it is actually in the vicinity of the cancer cell. Very much close to the cancer cell. It releases the drugs over time, not instantaneously. Obvious. If it releases all simultaneously, it's just like taking the drug, the free drug, which is give a side effect. Botak kepala, muntah, nausea and all those. And make it sick. It can kill the patient.
Oh, okay.
Yeah, that's a danger. I mean, the doctor have to give, because that will actually reduce the suffering of the patient. The drug actually very toxic. Okay, so the drug being released slowly. That one on separate. At the same time, heat can also help releasing of the drugs because of bilayer just now. Because of the bilayer, right? The bilayer is more flexible, is more fluid-like. So more drug being released.
Okay.
That's one way of doing it. And the upconversion particle can actually release the energy to the cancer cell.
Okay. You mean some various way to trigger the release of the
Yes,
drugs from
yes.
Oh, okay, I get it. Okay.
We cannot release the drug simultaneously, like burst effect. The burst effect, is toxic, kan?
Yeah, yes.
Yeah. If something which is toxic, you release it one by one, so it not become toxic
Oh,
because
okay.
because the amount is very, very small.
Okay. But if you inject the bilayer into the intravenous, through the intravenous,
Yeah, true.
the bilayer going to go anywhere in the body, right? Through the bloodstream.
Yes,
Then-
it can go 15-20 hours in the circulation.
Then the concentration will get lower. How you ensure it only go to the targeted organ or targeted site?
Because it has antibody just now that actually only stop at that particular area. Because in the blood circulation, right? It can stay up to 15-20 hours, right?
Yes.
Yeah, so it's only stop like like you have a hook, right? That hook only being caught at that particular area only.
Okay,
The rest of the area is not. Now the antibody like a hook, just suddenly you go to the area, suddenly it just nicely hooked.
Okay, I get you. Means you inject the antibody on the bilayer surface that targeted on the receptor of the cancer cells.
Yeah, we inject into the blood.
Oh, blood. Okay.
Yeah, and the liposome or the carrier will actually in the blood circulation.
Oh, okay. I get it. Okay.
So those like in Taiwan, for instance, suffering, let's say those in pancreatic cancers, for instance, very difficult to treat, isn't it? So we don't have that technology, but what they did is they introduced close to the pancreas area, right? So it won't go to the rest of the body. That's one way of doing it.
Oh, okay.
So it's not one treatment fit all kind of.
Oh.
So it depends on what's the problems of or where's the problem actually.
Okay, I get it. Okay.
Yeah.
Thank you, doctor.
No problem. Right? Anything else? Any question? So for the Muslim, selamat berpuasa, right? Maaf zahir batin, right? And the rest, well, I see you again virtually. Quite unfortunate that I don't see you face to face. Okay. If not, thank you very much. Okay, guys. Okay, you take care.
Thank you, doctor. You
Remember-
take care too.